per phase analysis. Now we are going to see about the per phase analysis. Why we are going for per phase, single phase analysis? Consider the transposed three-phase transmission line as shown in the figure. So what happens is we are dividing this one phase into three. That is for sometimes. So 1/3. Say for example, this is 1/3, this is 1/3, 1/3. Like we are dividing one phase into three. That is, we are taking, say for example, this is the first phase. First line, A line. So it is traveling for some distance. So again, it is traveling in the next, it is traveling in the distance in this distance. In this distance as A, and again it is move on to the this particular line and having the distance of A. That is a single one phase. Okay, so in the transposed that is called transposed. So for some distance, it is going in one phase. So again, it is going for one phase and one distance of A. Again, it is going to this particular A. Here again, it is going down to this particular A. Similarly, IB starting okay, B phase. So it is having the current IB for certain distance B. So again, it is going to this particular portion okay, for sometimes, and again it is moving to this phase. So that is called the transposed transposed line of phase B. Next is similarly phase C. You see, so it is traveling with a certain distance. Okay, certain distance as some distance D. Say for example D3. Okay, so having current as IC. So again it is move on to the this particular portion for some distance. Okay, so again it moves to the C. So this is called the transposed three-phase line. So here you see, you need to draw like this. Okay, first A phase you are starting. So again it is coming down. It is traveling to certain distance. Okay, the same A line again it is coming down. It's traveling to same A line. So okay, so A, B, and C having the distance of D1, D2, and D3. So here IA, IB, IC are the current flowing to the conductor A, B, and C. RA, RB, and RC are the resistance of the conductor A, B, and C. Next, LA, LB, and LC are the self-inductance of the conductor A, B, and C. MA, MB, MAB, MBC, MCA be the mutual inductance between the conductor, mutual inductance. So self-inductance means in that line, mutual inductance means between these two lines, MAB, MBC, MC. These are the mutual inductance between the conductors. So due to symmetry, due to condition symmetry, RA is equal to RB is equal to RC, because symmetry means all are having equal distance or are having equal impedance like that. So RA is equal to RB is equal to RC is equal to R ohms. Next, LA is equal to LB is equal to LC is equal to L Henry. Okay. Next, MAB is equal to MBC is equal to MC. That is mutual inductance between A and B. Mutual inductance between B and C is equal to mutual inductance between C and A. That is equal to capital M in Henrys. So for voltage drops along the three phases, del VA, change in the voltage del VA is equal to IA into R plus J into omega L into IA. That is J into omega L into IA is self-inductance. So this is mutual inductance. J into omega M into IB. M means mutual inductance. So this L means this self-impedance. M means mutual inductance. That is plus J into M into IB plus J into omega into M IC. So for A phase, so only you are having in the first phase, you are having self-inductance, and all other two phase having mutual inductance. Similarly, in the B phase, del VB is equal to IB into R plus J into, because Z is equal to R plus J into omega. Yeah, that already you know. But here, this L impedance will have two components. That is self-impedance and as well as mutual impedance. So that also we need to take into consideration. So here IB into R plus J into, so here IB into R plus J into omega L. This is for mutual, sorry, self-impedance for only B phase, because this is for B phase. So only B phase, and all other two are having mutual inductance, mutual inductance. That is J into omega into M into IA plus J into omega into M into IC. Similarly, del VC. Del V is equal to IC into R plus J into omega L into IC. That is self-impedance you are having in the C phase, mutual impedance you are having in the other two phase. That is J into omega M into IA plus J into omega into M into IB. Now, this equation, that is a previous equation, can be rewritten as like you can take the common terms outside. Del VA is equal to IA into R plus J into omega L plus J into omega M into IB plus IC. So here now you can see clearly. So this is the self-impedance, this is the mutual inductance. This is the self-inductance, this is the mutual inductance. That is R plus J into omega L. That is in only one phase. If you take A phase, that A phase alone having the self-impedance, other two phases B and C having the mutual inductance. Mutual inductance. So similarly VB. So I'm like that. IB, this only one phase having self inductance and other two phase having mutual inductance. Similarly BC. So in symmetrical circuit, IA plus IB plus IC is equal to 0. That you know. In symmetrical, all three currents IA plus IB is equal to IA plus IB plus IC is equal to 0. So that you substitute in this equation, and this equation becomes del VA is equal to, so this becomes 0. So IA into R plus J into omega L minus J into omega M minus J into omega M. So or otherwise you can write in this terms. IB plus IC is equal to minus IA. Okay, because IA plus IB plus IC is equal to 0. If you take this IB and IC alone, this will becomes minus IA. So like that also, if you substitute minus IA here, so instead of IB plus IC, you substitute minus IA here. You take IA common. So R plus J into omega L minus J into omega L. That is nothing but IA into ZP. So ZP is the impedance of that particular phase. What is ZP? Yeah, ZP is the phase impedance. Phase impedance, that is R plus J into omega L into L minus M. That is this term. R plus J into omega L minus J into omega M. Okay, so that term will change into per phase impedance, that is ZP. So similarly for all the phases, same IB. So del VB is equal to IB into ZP. Del VC is equal to IC into ZP. So similarly for all the phases, same thing. So now ZP is nothing but phase impedance. So that J omega is common here. That we are taking, J omega is common here. That we are taking outside. So R plus J into omega into L minus M. That is nothing but equal to R plus J into X. So rewriting this equation in the matrix form, that is this equation in the matrix form, if you rewrite, so here del VA, del VB, del VC. So here you will get ZP, ZP, ZP. This is all 0 into IA, IB, and IC. So this is nothing but the simple form. We can write like del into VP is equal to, that is all phases, phase voltage is equal to ZP into IP. ZP into IP. That is IA, IB, and IC in terms of peak current. Okay, coming to this phasor diagram in the symmetrical system. Symmetrical system. Say for example, VAR is the receiving end voltage. VAR is the receiving end voltage, and having the resistance of IA into R plus having the reactance of IA into X. Okay, so resultant. This resultant will have this resultant is the sending end voltage VAS. Okay, so this is the receiving end voltage. Receiving end voltage having the impedance. So definitely will have impedance. So that impedance will be divided into your resistance component and as well as the this reactance component. So R plus J into X. So here this is the resistant component, that is IAR. This is the reactance component, the IA into X. So resultant is VAS. So similarly for all phase, similarly you see all the phase for C also same. VCR. Okay, and having the resistant components and reactance components, resultant is sending end voltage. Okay, sending end voltage. So having the current IA, IC, and IB. So similarly for all. So this is the phasor diagram in the phase symmetrical system. Okay, phase symmetrical system. The phasor diagram subscript R and S refers to R refers to subscript and S refers to receiving and sending end voltage. R represents the sending end. Sorry, R represents the subscript and S refers to the receiving and sending end ends of the transmission line. So we noted that phase impedance matrix. Phase impedance matrix ZP is diagonal and all diagonal elements are 0. So phase impedance matrix where, yeah, this is phase impedance matrix. All the diagonal elements are equal. Phase impedance matrix ZP is diagonal and all the diagonal elements are equal. That is ZP, all are equal. So what are the assumptions here? That is a complete decoupling between all the three phases, because consider a phase del VA that depends upon IA only. Because why IA only? Because all components, del VA components, we are writing. There is no IB and IC. There is no coupling terms from the IB and IC, because all IA, IB and IC also we are rewriting in terms of IA. So there is no coupling terms for from IB and IC. So that is one of the assumptions here we are doing. Next, current poses the three-phase symmetry. That is, the voltage drops can be determined. Voltage drops can be determined. So what is the voltage drop? Because this is the drop. Because this is the sending, receiving end. This is the sending end. This is the drop that combines of your resistance and reactance. Okay, resistance and reactance. That is the drop. Resistance and reactance is the drop. So that is what here they said. As the current possesses the symmetrical, the voltage drops can be determined as corresponding phasors will be equal, except for 120-degree and 240-degree phase shifts in all three phases. We can obviously limit our analysis to one phase only. Because why one phase only? That you need to very careful, because all we are converting, all VA terms also say here, you see, all terms. The previous thing we have seen, no, all IA terms we are converting into only one phase. That is IB also we are converting in terms of IA, IC also we are converting in terms of IA, because then that is called the single phase. That is called single phase or per phase analysis. Only one phase analysis. So this is referred to as one phase. So why? What is the advantage of this per phase? Means calculations are easy. Why? Because all we are converting into one phase means there is no much calculation. Again, so if it is not in one phase, again you need to do for all the phases or separate calculation. That also there. So this is called the per phase analysis. So this is also sometimes 2 mark question they may get. What is per phase analysis? What are the assumptions that is made in per phase analysis? You'll get in your subjects. That is in power system analysis or computational methods in power system or advanced computation methods in power system. like advanced power system analysis. For all the subject, you will get this kind of questions as a 2 mark question per phase analysis. Sometimes in 5 marks also that derive the per phase analysis of a transposed three-phase transmission line, or derive the per phase analysis of a three-phase line. Like that, anything is asked, you just have to derive, not derive, just have to write all this phase voltage, phase currents, and in terms of what is the change in the voltage, and in terms of this phasor diagram, the symmetrical system, everything you need to draw on the assumption. With all the assumptions, you need to write for the per phase